Hey everybody, so just started this recording. We are doing topic 28 today. I think this is our third classification model. Yeah, third classification model, and it is Bayesian classification. Interestingly, even though I started this phase talking about gradient descent, like 2 out of 3 of the models that we've talked about so far don't use gradient descent. So this is another one of them. Yes, not yesterday's. They're Tuesdays, k-nearest neighbors. Again, not gradient descent either. It's really just looking at data points and where they are in space. And today's will be purely based on conditional probability, and we'll see how that is used in the context of classification. Very, very interesting. So a little bit of context about this model. It is based on the Bayes theorem, which we talked about back in phase 2, conditional probability. So naive Bayes classifiers are actually linear classifiers that are known for being simple yet very, very efficient. You'll see that if you're running this model on very, very large data sets, it usually outperforms other models in terms of time, because it's literally just computing probabilities across like your data, and we'll see how that is done. It is done very, very quickly. There's no iteration done in this model, and that's why it's very, very quick. So this probabilistic model of naive Bayes classifiers is based on Bayes' theorem, and the adjective naive comes from the assumption that features in a data set are mutually independent. Now, mutually independent just means that they are not related to each other at all. So in like prices of a house, I keep bringing that up because that was your last project, but in prices of a house, if you were to use like some sort of Bayesian model to predict prices of a house, the assumption will be that none of the features are related to each other, which doesn't make sense, right? Because let's say you have square footage, number of bedrooms, they're inherently related because more bedrooms you have, there is a strong assumption that the higher your square footage will be. But that's where the naive word comes from. This independence assumption is often violated because you can never get pure mutual independence between features, especially when they're all characteristics of a singular data point. So although this is always violated, naive Bayes classifiers still tend to perform very, very well under this unrealistic assumption. Especially for small sample sizes, naive Bayes classifiers can start to outperform more powerful alternatives. As we get more and more into classification, the concepts of classification, it'll sort of bring to light why just using probability can be stronger than using machine learning. So today we'll be going through some really quick examples of doing naive Bayes classification. These examples are actually using text. And the reason for that is because naive Bayes is a model that is known to perform very, very well and efficiently on text data. Unfortunately, we won't get into the weeds of text data until next phase. However, one way to think about it is if you have text data, every unique word is a feature. That's one of the ways that you can deal with text data. We'll actually see how that works. But if you just have, data with other features that isn't text, it works exactly the same way. I just do think it is in some ways simpler to explain naive Bayes with text examples. So we're going to be doing it using this example. So let's just say our classification problem is we have a bunch of news headlines or statements, some on sports, some on politics, and we want to train a model to be able to recognize if you give it some input text, whether it is more sports or more politics. So as some examples, some sports statements we have here, the match was close, coaches agreed on strategy, played in a sold out stadium. These are sports topics. Now this politics examples, we have world leaders met last week, the election was close, and officials agreed on a compromise. The test statement seems a little bit ambiguous because it's the world leaders agreed to fund the stadium. Now, arguably, this could be in either one, but we'll take a look to see, like under naive Bayes, how would this be classified? So let's go back to think about Bayes' theorem. So how I always remember Bayes' theorem is in a probability context when you have conditional probability of like A given B, and you need to figure out B given A. Whenever you need to figure out the flipped conditional probability, you would use Bayes' theorem. Now, that's coming from me with a history of solving math problems for hours on end. But in thinking of it in more of a contextual sense, this is how you can break up Bayes' theorem. So what we want to think of is what we want to predict is the posterior probability. And we will look at this in the context of a classification problem in a little bit. But you can think of the components of Bayes' theorem as so as well. So here we have the likelihood, and likelihood is actually very similar to the likelihood from maximum likelihood estimation, but we don't really have to think about it that way. We can look at the class prior probability. So basically, out of all of our rows of text, what's the proportion of, your text belonging in this class versus a different class, literally like your class balance. And then predictor prior probability. In the context of classification, you can think of it like this. The probability of a data point labeling. So let's just say that, we have two classes, L1 and L2, L1 being sports, L2 being politics. If we want to find the probability of a data point being classified as sports, given its features, given, the text that it's in it, we can compute that by taking the probability of the features occurring, given that they are sports topics, multiplied by the probability of the label, probability of an article being sports, divided by the probability of features. So if we're trying to decide between probability of sports and probability of politics, we can actually rework this equation to turn it into some sort of ratio. So here you can see that if we have L1 and L2, we're pretty much taking two versions of this equation and stacking them on top of each other. So the L1 version is on top. So probability of L1 given features is equal to P features given L1 times P of L1. And then same for L2. And eventually the P features ends up canceling out. Based on this result over here, based on what that number ends up being, we can actually figure out whether it is more sports or more politics, right? If this number is greater than 1, it's going to be a whatever L1 is. And if the number is smaller than 1, it will be L2. So that's one way that we can figure out the probability of, or figure out the classification of a certain data point. So in the context of our problem, this is how we would break up the naive Bayes equations. Let me zoom in a little bit more. We have the probability of a document being in politics, given its features, is given by this equation. The probability of it being sports, given its features, is given by this equation, and we can combine the two. Probability of document cancels out, and we have this ratio over here. All right, so any questions at this point in relating the Bayes' theorem to the task we're about to do? Okay, so let's break this equation down, and we'll start with the easier parts and then work our way up to the harder parts. So first, how do we calculate P politics? And similarly, we're also going to have to calculate the probability of sports. Well, that's very, very straightforward. It is literally just the number of politics documents out of all the documents. So here, if we run the cell, well, let me make sure I ran everything first. Okay, there we go. All right. So these are our politics texts. And similar, we can do the same thing for sports. Probability of politics, because we have 6 documents in total, 3 of each. They are both going to work out to 0.5. So this part's very, very simple. Number of whatever documents out of all the documents. So in this case, both of them will be 0.5. This part gets a little bit trickier. How do we calculate the probability of a document occurring, given that is politics? So this requires us to look at all of those politics documents to figure out what the probability of a document is occurring, which I know seems a little bit abstract, but we'll see how this is helpful for us. So let's take a look at this test statement. Remember that this is our ambiguous test statement. So if we break it down from document to phrase, so the probability of a phrase occurring, given that it's politics, is the product of the probability of each word occurring, given that it is politics. So thinking of it as a phrase is a little bit tricky, because in words, each word is like a different feature. So it's better to think of it as words rather than phrase. So for every unique word that occurs in a phrase, we're going to look for that probability, given that it's in politics. So we can break this down even more to say that the probability of a word occurring, given that it is a politics document, is the number of that word in all politics documents out of the number of total words in politics documents. So you can sort of think of it as like, if you take all of the politics documents and put all of their words into a list and take a value count of that and take a normalized value count of that, that will be this number. Does that make sense? Cool. So what if you see a word in your statement that your model hasn't encountered before? So if there's like a random word like, I don't know, trees isn't in our training data. If we see a random word there, the numerator ends up becoming 0. Any questions at this point? Mo, I saw you came off of mute.
Yeah. When you say documents, what are you referring to? The phrase? Are you referring to the words?
Great clarification. So by documents, I literally mean each of these is a document / phrase. I guess I should be more consistent with that. But when I'm referring to politics documents, I'm referring to this collection.
Okay.
So if I want to look for the probability of the word the occurring out of all the politics documents, it's literally 2. Is there any other the? Yeah, it's 2 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 2 out of 15.
Okay. I got you.
And you can, yeah. So you pretty much want to do the same thing for every word. However, where was I? Cool. If there's a word in your test statement that the model hasn't encountered before, the numerator becomes 0. And that becomes a bit of a problem because we are doing this for every word. And where's my pen over here? This part we're doing for every word. So every word, we're going to take their probabilities and we're actually going to multiply them with each other. So it is a problem if we have a word that we haven't seen before, because then that one probability becomes 0. And when you multiply 0 with anything, everything just becomes 0. So we cannot have 0 as a numerator. So therefore, we introduced this thing known as Laplace smoothing. The whole thing of Laplace smoothing, it is used in multiple different contexts in math, but what's important for us to know, you can sort of think of it as kind of regularization, a little. It's not exactly, but in some ways it's very similar to regularization. And when you take a look at your naive Bayes models from scikit-learn, this is the hyperparameter that you end up tuning. So we do Laplace smoothing where you add this alpha. So let me actually clear all of this so I can scroll down a little bit. Okay, so to stop things from going to 0, you add alpha on the top, and then you add alpha times d at the bottom. So alpha is any sort of number that you want. I think the default is, the default I think is 1, but you can actually change this to be any constant you'd like. The bigger the number, the more smoothing, or you can also think of it as the more regularization. And then you do alpha times d. So, and d is basically the number of features that you have, basically like however many columns you end up with your data frame. So now this equation ends up becoming this equation just in case, so that we won't have any zeros at all. Cool. Now we have that. We basically have to do this for every unique word that we have. And then we end up with, we can basically multiply all of those probabilities together to end up with the probability of the phrase occurring. All right, so next, we don't need to calculate the probability of the document. If you remember, that's the part that cancels out. So we're just going to replicate this process in a little bit. So it's not very important. Again, why this is naive. Remember the naive part of naive Bayes, literally why they're using the word naive is because we are not following the assumption that features are independent of each other. So just something to keep in mind. Cool. So we're going to apply our equations and we're going to do this like this. These are all of our training data points, or we can just assume that these 6 phrases are our training data. So with this training data, let's just take a word count so far, because we do need to look at the frequency of words anyways, right? So frequency of words in docs. So we're going to take a look at the word counts. So this is the word counts for both for all of our training data for sports or politics. And you can see some words only occur in one, some words occur in both, some words only occur in the other. All right, so with this, we also have our test sentence. So we're going to start building out our probabilities based on these word counts. So let's do this word by word for every word in our test sentence. So, okay, first we're looking at world. So world appears one time in politics, I think. Yeah, one time in politics, 0 times in sports. And let me zoom in over here. So one time in politics, 0 times in sports. And you're doing this +1 for the Laplace smoothing. And we're +30 over here because +30 is because there's 30 unique words. This 15 over here, I believe, is the total number of words in politics documents. So basically the number of words that are not 0 over here is 15. So that's where all of those numbers come from. And so the probability of world happening, given that it's politics, is 2 out of 45. Probability of world happening, given that it's sports, is 1 out of 45. So with all these probabilities, we can do the same thing for every word. Basically, these numbers will correspond, these first numbers on the numerator will correspond with these word counts up here. 15 is the number of unique words per that class, and 30 and 1 are the smoothing numbers. And you end up with these probabilities over here. So these are the word probabilities. And we remember to get from, sorry, I messed up the zoom a little bit. All right. So with these probabilities, these are word probabilities, and to go from word to phrase probabilities, we just have to multiply them all together. So to multiply them together, and this is because of this part, where this just means take the product of all of those things. We're going to multiply these together, and this number is going to end up being very, very small. So after we do that, and basically this is to help us compute the math, we're going to do this super quick. This, by the way, is literally what we've done over here. So we're going to do this super quick. This is the word count, finding the likelihood. Okay, cool. So we have the likelihood of sports and then the likelihood of politics, just like that. So the likelihood of sports, you can see, is 1.53 times 10 to the power of -10. And the likelihood of politics is 3.06 times 10 to the power of -10. You can take a ratio of this, like I mentioned before. You can take a ratio and, sorry, it's so much scrolling. You can take a ratio and figure out whether it is politics or sports, depending on how you're doing the division, or you can pretty much just compare those likelihood numbers. So based on that, looking at the likelihood numbers, it looks like politics is a lot more, well, it's about 3 times more likely than sports. And just based on that calculation, we will say that that test statement is more likely to be a politics document versus a sports document. And that is how naive Bayes is done. It's just a little bit of calculation through this process over here, multiply them all out together, compare the probabilities, and that's how the classification is done. Even better, we actually don't need to do any of that calculation on our own. So these functions, feel free to look through them if you'd like, but I don't think it's that important. It's literally just translating all of this math into this. So yeah, any questions at this point? We're going to go through a little bit of implementation below, but any questions at this point about how the algorithm works?
Yeah, just to clarify, the 30 is the smoothing,
Yes. So because there are 30 unique words, if you see that the Laplace smoothing, it is alpha times D. So alpha is 1 and D is 30, so it will +30. If your alpha was 2, you would do +2 over here and then +60 over here. And you can sort of think of that as a little bit more regularization happening.
All right, thank you.
You're welcome. Yeah, so it's literally an application of Bayes' theorem. There are a couple variations of naive Bayes. Like if you actually take a look, and let me pull up this document again, the summary of the phase 3 models. So if I zoom into naive Bayes, there's 3 different kinds of naive Bayes. There's Gaussian naive, Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. Off the top of my head, I don't remember which one is which. But I think multinomial one is the one that's used the most, or Gaussian. Actually, yeah, don't take my word for it. There are 3 different ones. Right on the top of each one in their documentation, they actually mention what use cases they are, but they all work very, very similarly. You're not going to get huge differences in your test results if you use a different one. I just think that I think multinomial naive Bayes works better if you have more than binary classification, I think. But yes. Okay. Oh, I'm going to go through this later. Cool. So let's do some really quick implementation. Oh, before that, some pros and cons. Okay, so pros. That math was very, very quick. It's much faster. I mean, we already talked about how gradient descent does scale very well, but this is literally applying probability equations to your fixed data set. So there's no iteration, and it's even faster than gradient descent. So it's very, very efficient to predict classes for your test data set, and it does perform well in multi-class prediction because it is probability based. It's really just based on how your data is distributed, based on you can think of it as literally based on their normalized value counts. It's just assigning, okay, this data point looks more like the sports data points that we already have, or looks more like the politics data points that we already have, and does that classification based on those probabilities. Also, when the assumption of independence holds, so when you do have data that happens to be independent of each other, a naive Bayes classifier does require much less training data and can perform a lot better than other models like just logistic regression. Also performs better with categorical inputs. For categorical inputs, if you think about the way that text data is, and I'll show you an example in a little bit, but if you had every word being a column, it's very, very similar to categorical data. We'll take a look in a little bit. For numerical input, one has to assume a normal distribution, but again, this assumption is often violated as well. So some cons. It is a bad estimator. It is not a great estimator. So the outputs from predict-proba are not to be taken too seriously. Now, that doesn't mean it's not good at classifying. It's just not good at estimating, which these are 2 very similar but different things. And what they mean by this is the probability of something being politics and probability of something being sports is very, very, very small. So it's really all about relative probabilities that is used to make the classification. But these probabilities don't sound right? I mean, it has to be either sports or politics, right? But the fact that these numbers are much smaller doesn't really make sense. Also, the con is it is naive, assuming independent predictors, but in real life, it is almost impossible that we get completely independent features. So that is kind of a con, but it's actually a con that doesn't affect us too much in most cases. Cool. All right, so for implementation, we are going to use a couple things. So I'm going to use this news data set within scikit-learn. I'm also going to be using this thing called a count vectorizer, which we'll talk more about in phase 4, but it's a quick way to get that, is a quick way to turn our text data into numerical form. And I'll show you what that looks like in a bit too. And we have our usual metrics as well. Let me make sure I run this. And let's grab our data. So this is what our data looks like. We have some train and test data over here. And what our train data looks like, is kind of messy for now, but you can see that there's a mixture of, what's target 0? I think target 0 might be sports and 1 might be politics. We'll figure that out as we go. Yeah, Dodgers sports. Okay, there we go. All right, so here we have a bunch of text data and does not look very clean, but we'll deal with that when we get to NLP. And then we have targets as well. If we look at the targets, okay, yeah. 0 is for baseball, 1 is for miscellaneous politics. So let's take a look at the info. You can see that here we only have 2 columns, just because we have our target column and then all of our text is lumped into one singular column as well. So if we look at our value counts for our target, it's fairly evenly spread out, maybe a little bit more on the sports than in the politics, but that's okay. And an example of what it looks like, this is what our text looks like. In the next phase, we'll talk more about ways that we can clean this up and maybe not have so much noise in our data, but for now, we'll take this for granted. Okay. So what we're doing is we're first going to vectorize our text. Now, this is, again, something we'll talk about more about when we get to NLP, natural language processing. but we need to get our text into some numerical format. And what this count vectorizer does, I mean, kind of as the name suggests, it basically gives you word counts for each of your data points. So what this will look like is, this is not very clean. Actually, let's look at the first 20. Hopefully there's more information. Okay, well, can't really see anything over here, but basically the columns, and let me show you all the columns then. There are almost 20,000 columns, and each column represents a unique word that appears in our data set. So that means there are almost 20,000 unique words in our data set. And under each of these columns, so if we take a look at this, there's basically a word count. So let's maybe take a look at, is there the word the? Okay, cool. So if I look at the column, you can see the word count. So the word the appears 42 times in the first article, 3 times in the last article. So that is what this data looks like at this moment. As of right now, this can be a little bit overwhelming, but you can literally just think of the fact that maybe you just have 20,000 features in your data set. That's one way that you can look at this data for now, because I know 20,000 columns sounds like a lot, but just imagine that you have 20,000 features for your data. And a lot of them are going to be 0 because, again, not every row has every word in it. So you're going to see a lot of zeros in this data, which actually makes your computation for naive Bayes easier. All right, so we look at the sum. This is kind of like a word count, a total word count. So apparently 00 appears 227 times, 000 140 times. So if you're interested to see the sum, maybe we can take a look at does head work on this? Okay, cool. I guess this is not very informative for us either. Yeah, as for right now, there's still a lot of noise in this data, which we're not going to worry about for now. Let's get rid of this. Okay, so yeah, that's just number 42. So similar to what we were doing before, we're going to set our Y train and Y test, which comes from DF train and DF test. And we are just going to instantiate our model. Again, very similar to the modeling processes that we've been doing already. Fit our X train and Y train and make predictions on our test set. Actually, since we're here, let me make predictions on our train set as well. X train and Y train preds and then Y test preds. Cool. So that has already trained, even though we had 20,000 columns, it almost instantly, there was a minor like 1 second lag, but it's already trained our models. And if we take a look at our confusion matrix, this is the confusion matrix for our train set. So we take a look at our test metrics. Oh, I should reorder this. Oh, these are train metrics. Okay. All right, well, I'll deal with that later. Our train metrics, perfect. There's perfect classification in our train set. And in our test set, you can see that there's a little bit of misclassification over there, maybe a little bit of overfitting as well. And Y preds, it should be Y test preds. So let me actually change this back. Okay, there we go. So these are our test scores. So just like that, we get the same metrics that we've been getting for our past couple of models, but now we've also done it on text data. I will say that naive Bayes is not only to be used on text data. So for all of your projects, you can definitely implement naive Bayes as well. And as usual, I want to see all of the metrics like I've been mentioning, confusion matrix and that classification report. I know this is not the classification report, but I'm going to show you all that in a little bit as well. One quick thing to note out of naive Bayes, actually, let me pull out the Gaussian naive Bayes. B, scikit-learn. So from here, there are a couple things that you can pull out. One thing that you can pull out is the predict proba to get the probability estimates for a test vector. So one thing that you can do is, sorry, I keep going to the wrong notebook, is if I'm doing predict log proba of my X test, or you can do this for X train as well, this will just be the relative probabilities of each class. So you can see that this will kind of correspond to, I think it's Y preds. Cool. So you see how this ends up being 1, 1, 0, 1, 1. It's because this number is greater than this negative number. This number is greater than this. This is negative, so it would be 0. and then these numbers are bigger as well. So based on this, you can sort of see if you wanted to ever see like the relative probability. And in this case, I guess it's pretty clear cut since you have a lot of zeros over here. You want to see like how close was it to being sports or politics. You can actually take a look at this if you would like. But yeah, any questions on naive Bayes? Cool. Again, like naive Bayes is usually, it's if you have text data, naive Bayes would be one to definitely try out and use.
I have a quick question. Does it make sense in this model to keep the words, the A, N, and like the ones that are really common and like everywhere?
Yeah, good instinct. No.
Okay.
It doesn't make sense to keep that because you, I'm going to talk more about the whole concept of separability of data when we get more into the project. But basically, these words are noise. They're not really semantically important. And so like those words will likely not lead you towards like politics or sports, unless you're doing something that has like, you know, those filler words more often than not, then you could consider keeping them but for most things, you actually do want to clean those words out. But that's more of like an NLP pre-processing thing, which we'll talk about next phase.
Okay, no problem. Thank you.
You're welcome. Mo, you have a question?
Yeah, I think you may have already answered this, but for this classification model, you can't, are you able to use it for numerical data, or is just
Absolutely. Any data at all. I'm actually going to show you all. I want to talk about this function task that I have for you. I'll actually show you. We can use naive Bayes on that data set as well.
All right. Thank you.
Cool. All right. Any other questions on naive Bayes before I move on to this assignment that I want you all to start working on? Cool. Okay, so the thing that I want you all to work on is to basically write a function that automates the modeling process. So I've actually made this notebook for you all. It is on your repo, but I'm gonna drop it. I'm gonna drop this link into your in your Slack channel just so it's easier in case y'all don't want to deal with like pulling down the repo. You also don't have to submit this notebook to me. The only thing I want you all to send to me is the function, which I'll show you all later. I'm going to briefly go through this notebook because I would like you to read this on your own as well. But the idea here is we've seen that all of these scikit-learn models are used the exact same way. It's always instantiation, fitting our model, make predictions, confusion matrix, other metrics for train and test. So it's pretty much the same thing over and over again. And for your projects, I do not want to see a bunch of the same code copied and pasted. So instead of doing the same code copied and pasted, I would like you all to write a function that can replicate this for any model. Now, in this notebook, I've given you all kind of like a starter on how you can build this function, but feel free to tweak this function as much as you like. You definitely don't have to follow the same format, but it just has to make your code less redundant. So to start, these are libraries that I'm just starting off with. Of course, you can import whatever you think is necessary. And to just try out this function, we're going to use this fairly simple data set. So this data set is on banknote authentication, and I left some space for you to inspect your data so we can actually take a look at DF. And basically, this is for real versus forged banknotes. And you have variance, skewness, kurtosis, entropy. I don't know why these are used to verify banknotes, but this is the data set. And I think I wrote somewhere that class 0 is authentic and class 1 is forged. So what this data is, for this mini assignment, I don't care about the EDA. I just care about you automating the process of modeling. So inspect it all you want, but you don't have to get into the EDA. There is no null values in this either, so you don't have to worry about that. I just want you to be able to automate your modeling. So the things that I want to see are confusion matrices and the classification report for both the train and test set. So we're going to start with the decision tree classifier, which is actually the model that we're going to talk about on Saturday. Actually, since we're doing naive Bayes, I can switch it to naive Bayes real quick. So let's just grab our naive Bayes model. Where did I put it? Naive Bayes. Okay, over here. So let's start with this, and then instead we will do a Gaussian naive Bayes model. And I'll show that this is, this can be done on numerical data as well. So let me just change this real quick so that we can run it with no errors. Okay, so just like that, and that was pretty immediate. We've instantiated our naive Bayes model, fit X train, Y train, predict on X train, and predict on X test. We're going to print our classification reports for train and test, and you can see not super great. If you want, you can make this even more fancy. You can even put in like print statements saying classification report for a train set. You can pretty much do whatever you want. If you want to make it like a new line character, you just do /n to add an extra space there. You can, yeah, really do whatever you want with these printouts. And then I want to see this, and I also want to see confusion matrices. So I set it up this way. Feel free to use this as well. I don't care if you use this code, but this just turns into subplots so you can have them side by side. If you want custom colors, you can go and do that as well. But you can see here, I have my confusion matrix for both my train and my test set. For your modeling project and for any modeling that you want to do, these are the main metrics that you're going to be looking at. So I want you to incorporate this. So in this notebook, this is all set up for you. In the version that I'm going to send over, it has decision tree, which is the model we're going to talk about on Saturday. But I mean, the implementation is exactly the same. So even if you don't know how decision tree works right now, you can still implement it. So basically you have these outputs that you're going to want to replicate. Now I put this section here to replicate all of those steps, but just with a completely different model. So basically you can copy and paste that and just replace all of the naive Bayes or decision trees with a random forest model. And random forest, you can see that I imported that here. So based on that, you can either look it up or figure out how to instantiate and use a random forest. So just like that, you can see that doing two models takes up a bunch of cells, right? Like 1, 2, 3, I guess 3 cells per model. For our project, some people have been running like 10 to 15 models. And so you can imagine that becomes extremely repetitive. So the main thing I want you all to do is to write a function that can run the model and print the metrics for you. I'm not going to do this right now, because you are going to do this as an assignment. I've started out this function for you that takes in the model, X train, Y train, X test, Y test. How I suggest that you use this function is you instantiate the model here. And here I put it as test model. You should be able to instantiate a model and successfully run this model. So what about all of these printouts? You pretty much have to put your print statements for your classification report in here. Also put your plotting of your confusion matrices here as well. With those inside the function, every time you call run model, everything will output all at once. It'll make your notebook a lot more streamlined. Questions about this function? I do think it's easier if you do like hands-on trial and error. Happy to talk about it at one-on-ones as well. Yeah, Nelson?
Would you recommend doing the imports within the function or outside?
Good question. Do not do the imports inside the function. Do it outside.
Okay.
Yeah, so I've imported most of what you need up here already. So just leave that there. Cool.
Gotcha.
Any other questions?
This is this up yet or is not up yet?
This is up on the repo already. So 4.5, I think if you go into here and you go into phase 3, it is under phase 3 function. And so this is exactly the same notebook that I'm going through right now.
All right.
Cool. Okay, so a couple details that I do want to talk about. You notice here that at the end of my function, I'm returning the model object. And I do want to talk a little bit about why we return this model object. So as you saw in our last here at naive Bayes over here in our last cell, we grabbed these probabilities out of the model. Now, if we're just doing the model within a function, and we're not returning the model, there's no way for us to access this information. I'm going to run through an example that is more relevant for decision trees that we'll talk about on Saturday, but the same thing holds. You just want to be able to access these methods and attributes from the model itself. So as an example, I have this decision tree over here. I know we haven't talked about decision trees yet, but let me just fit it to X train and Y train. Something really neat about decision trees that if you all decide to use a decision tree in your projects, I do want to see this as well. Something very neat about decision trees, it has this attribute known as feature importances, which literally will tell you what is an important feature for classification in your data. So if I do feature importances, you can see here that it gives me an array of relative importance. So what you'll do, and I'll talk more about this actually on Saturday as well, but what you can do is you can see, all right, these are my features, these are how important they are. And then I can actually plot them. So if I were to do, and you can see that this is not through a function yet. If I were to return my model in my function, that means that after I use this run model function and I set that to a variable, so if I do variable equal to run model, blah, 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 I will be able to access this information through variable.featureImportances, as long as you return that model object at the end of the function. So don't forget to return the model object. Basically, that's one of the things I'm going to be looking out for as well. If this doesn't make sense yet, once you're in the midst of writing your function, I'm more than happy to like talk through what exactly this means. But when in doubt, just know that at the very end of your function, you want to return model. And very likely it would be like print classification report of, you know, whatever it is, that syntax. You want to basically print that. So that's very, very likely what this function is going to look like. Cool. Any questions at this point? All right, well, when is this due? There is no due date. I am not a big believer in due dates, but just before you start working on the project, because once you have this function done, the main bulk of your project will just be do some EDA, use the function that you would have already written, and then just do your evaluation and interpretation. And that will be your project. It will just make it so much easier. But if you just write your function using this random data, it should be applicable to any other data that you use, because pretty much it will draw on whatever your X train, Y train, X test, Y test is. And as long as you're doing your data cleaning correctly and there are no null values and they're all numerical, this should work on any data at all. Cool. At the very end here, I have a couple like guidelines for scripting. I'll talk more about scripting at an office hour for the project, but just in case you wanted, because I did talk about scripting a little bit last phase, just in case you wanted to do a little bit of that, read these 3 lines, I guess, and then you can try to see if the scripting does work. And I think, oh yeah, to Nelson, your point about like where your import statements go. If you're doing this, your import statements still don't go inside your function, but go at the top of your script.
Gotcha.
Welcome. All right, well, that's all I wanted to share for today. This notebook, I'm going to put it in a zip file with the data CSV and just throw it into our Slack channel, just so you don't have to work out of the study group repo. But you can also work out a study group repo if you want. Cool. Any questions for today? Go once, going twice. All right, well, if there's nothing else, the next study group will be, again, Saturday at noon Eastern time, which I know is early for y'all on like the West Coast / Mountain time. So apologies about that. It will be recorded. So, but anyways, I do want to get some more models out of the way before we introduce the project next Tuesday. And also next week, it will only be a study group on project introduction and pipelines technically. But yeah, that'll be helpful. And I think it will really set y'all up for a smooth project process, fingers crossed. Cool. Well, if there are no further questions, I will see you all here on Saturday at noon. But yeah, anything as usual, Slack me and let me know. All right. Have a good rest of your evening, everybody.
Thank
Bye.
you. Have a good one.
Hi, guys.